The name of this video is Electrostatic Shields Dual. Let us suppose to consider a homogeneous conducting material in normal conditions and in macroscopic electrostatic equilibrium, MEE, as always. For example, a hollow block of copper. This is the region where the copper is confined, and there is a vacuum inner cavity. The copper block outside here, we call it capital gamma 2. It is characterized by an external surface, a capital sigma external 2, as well as an internal surface, capital sigma internal 2. We hypothesize that this conducting object is initially uncharged. That is in the neutral state. Remember charge conservation principle. We further assume that within the inner cavity of this object, there is vacuum here and vacuum outside. In this vacuum inside, there is another object, not hollow, for example. It's a solid object, which in this case we call capital gamma 2, 1, capital gamma 1, to distinguish it from capital gamma 2, which is outside. The external surface of this object, obviously we call it capital sigma external 1. So object 1, object 2. That is why I call this 2, because I want to start from 1 inside. Let us hypothesize that the inner object is charged with a positive charge plus Q. So let's say we have 1, 2, 3, 4 charges. This is a positive charge Q on the inner object. Capital gamma 1. Okay. As we know, since everything, including the object capital gamma 1, is considered to be in macroscopic electrostatic equilibrium, obviously the charge Q can only distribute on capital sigma external 1, on the outer skin of capital gamma 1. Now, let us suppose to consider, as always, a Gaussian surface, which is a closed surface. I will do it in dash green, as follows. This Gaussian surface, as in a previous video, we hypothesize that it is entirely contained within the bulk of capital gamma 2, which again is in macroscopic electrostatic equilibrium. So we know that within this object, the electrostatic field, where this dash line is defined, has to be equal identically to 0 because of the ME condition, which we write up here. Not to forget, everything is in ME. That is both capital gamma 1 and capital gamma 2. All right, so the electrostatic field has to be 0. This dash line, we call it capital sigma, and is entirely contained within capital gamma 2, the bulk of that object. We can now use Gauss's theorem, and we know that the surface integral on the closed surface capital sigma, which is the flux through capital sigma of E dot NdA, since we are considering capital sigma to be entirely confined within capital gamma 2, obviously E is 0, as we've written here. Therefore, the result of this integral has to be 0. But we also know from Gauss's theorem, from the physics of the problem, we know that this has to be nothing but the total charge Q contained within capital sigma. So this symbol here, Q on something which is smaller or equal to capital sigma, means all the charge contained within this dashed green line here, divided by epsilon naught. This is the result of Gauss's theorem. But we know it has to be equal to 0. So now, let's look a little bit closer to this structure. So within capital sigma, what do we have? We have a part of, let's do this in green. we have a part of gamma 2, like for example all this part here, or all this part here, etc., where obviously there is no charge, macroscopic electrostatic equilibrium. Then we have a region where there is vacuum, where of course there is vacuum, so no charge. We then have the inner object where there is a charge plus Q. The only other spot where, the only other region where there can be a charge non-equal to 0, different than 0, that is, it has to be right on this boundary, which is capital sigma internal 2. That is the only place where there could be another charge in ME. And in fact, there must be, because this sum has to be equal to 0. So this implies necessarily that the charge contained on capital sigma internal 2 has to be equal to exactly minus Q. Okay, so if you have 4 pluses, there will be 4 minuses here, somehow in this fashion. Okay, all on this capital sigma internal 2. So obviously, this results in an electrostatic field where the field lines, for example, go as follows. This is E, different than 0, within the vacuum region. So here, for example, we go like this, from plus to minus, from plus to minus, and from plus to minus. So there is a non-zero electrostatic field within this vacuum region, okay? Which typically we call the vacuum region, we call it capital omega in all these Shields problems. Okay, and outside there's also vacuum. Okay, so this one was Gauss's theorem. Gauss's theorem results, this condition here is called total electrostatic induction. Total electrostatic induction. So let's write it down here. Note that this is a very important result, which is key in all has to do with capacitor. So see capacitors later on. Whenever you attempt to make experimentally to build a capacitor, you want to make it in such a way that total, and let me underline this, total electrostatic induction happens so that the whole charge on the inner object is entirely induced on, with negative sign of course, on the inner surface of the external object. Okay, so that's total electrostatic induction. The other property which we need to use here to solve this problem is a charge conservation principle. So charge conservation principle. You've seen this in the very beginning of this course when we discussed about electrostatic charge, very briefly. So it simply tells us that charge has to be conserved. Okay, so let us use this principle, that charge has to be conserved. In fact, Benjamin Franklin was one of the first to figure out that charge has to be conserved. Let's try to use it in this specific case. So if we began with an uncharged capital gamma 2 object, okay, there is a semicolon, ME is for both, uncharged is only capital gamma 2. Let's be specific here, so don't make mistakes. Gamma 2 has to be uncharged. But now, in a sudden, because of Gauss's theorem and total electrostatic induction, we have a charge minus Q on the inner surface, capital sigma internal 2 of this object. So in order to have a zero overall charge, it has to be that where the charge can go. Of course, it cannot go in the bulk of capital gamma 2 because of ME conditions, so it can only be on the capital sigma internal 2 and the external 2, which means Q on capital sigma internal 2 plus Q on capital sigma external 2, this is equal to nothing but capital Q on sigma internal 2, we already calculated this, minus Q, plus our unknown. Actually, let's do this one in red to be consistent, because Q is positive, and we do it in orange, so let's do this in red. So it's minus Q in red. And now there must be an unknown quantity, X, which is this charge here. Okay, so this quantity has to sum up to 0, which clearly implies that X, let's do this one in orange because we go back to a positive sign, x, which is nothing but this quantity here, q on capital sigma external 2 has to be equal to the opposite of that, that is plus q. As much as the original plus q here positive was on the inner object. So we must have 1, 2, 3, 4 positive charges on the outer skin of this object because of charge conservation principle. Great. So now this is actually quite interesting because you may have heard that electrostatic shields function both ways. They work both ways. That is, we have seen in a previous video that if I apply a charge on the external surface of this object, if we were living inside this object, we wouldn't know that there was such a charge, because this charge only distributes on the outer skin of the object. We have proven this in two different ways, integral and differential form. Now, in a sudden, you heard again, I'm sure, from many textbooks and videos, that, and other videos, not mine, that it has to work also the other way around. But now it seems that this is not true. So it seems I found a counterexample where this is not true. So in this case, it seems that if I place a charged object within this electrostatic shield with a positive charge, effectively this propagates all the way to the outer world where I see a positive charge. So somehow there is an electrostatic field outside this object pointing in this direction to infinite, everywhere there is a charge here. And so it seems that the electrostatic shield is not functioning both ways, because if I place something inside, I affect the world outside. However, the key that you need to realize here is that in order to place this object, capital gamma 1, within the shield, at some point in time, I had to break somewhere to open, at some point in time, t, I had to open this object to place capital gamma 1 within. This opening results effectively in the key word here, which is communication. In other words, I need to communicate between the inner region, capital omega, which is vacuum, and the outer world. So there is a communication with the universe, if you want. And in fact, it's this communication which effectively results in what? In grabbing some charge from the outer world and bringing it inside. So I need to take some positive charge from somewhere, from a source outside. I take this positive charge and I bring it within my opening in here. It's this communication that allows me to place such an object, a charged object, within the electrostatic shield. So obviously, the shield was not shielding anymore because I had to open it. So it's this communication channel which effectively results in this apparently paradox where the inner object effectively does some effect on the outside world. Okay, but now suppose that we are in a situation for t larger than 0. Okay, so this is the initial time t equals 0. So we are at a time larger than 0 where effectively we close this opening. And we have capital gamma 1 inside. So now the shield has to work both ways. So is it true that if I move around capital gamma 1 or I split it in two, keeping the same charge capital Q inside, will this affect, will any of these operations affect what's going on in the outside world? The answer is no. Two things we need to prove here. So first off, let's simplify this object to spheres. So let's consider a hollow sphere with a certain thickness. Within this sphere, let's put concentric with this sphere with the same center O, another sphere which is a hard sphere, conducting. So it's the same thing but with spheres. So let's call this radius capital R1, this radius, let's call it capital R2, and finally this radius, let's call it capital R3. Note that this region is completely full with a conducting material, and this region is also completely full with a conducting material. This is vacuum, so this is capital omega if you want. And I'm not going to sketch all the surfaces which are named exactly in the same fashion as here. So let's suppose again that we have a positive charge, 1, 2, 3, 4 positive charges on the inner sphere. complete total electrostatic induction and will result in minus and minus and minus and minus on the inner skin of the outer sphere, and charge conservation, of course, plus, 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 and plus. Okay, so it's the same thing but with spheres, okay? All right, so now let's see what happens here. First thing I want to show. Let us calculate the electrostatic field at each point, capital P, within capital gamma 2, which in this case is this region here. Okay, so in this case, the electrostatic field, well, we know that the outer shell, if you want, so where the charge plus Q is located, okay, which is here, all right, in this point, on this external surface, obviously this behaves as a shell, so we know that inside the shell, this charge distribution has a zero field. So the only field in this point has to be due to this hard sphere with a positive charge and to this shell with a negative charge. So we do superposition principle, and we see that for each point, capital P in capital gamma 2, in this case of spheres, in this specific case, then we obtain that Coulomb's law and superposition principle, 1 over 4 pi epsilon naught. We can calculate the electrostatic field or potential, let's do the field. So this has to be the total charge within the inner sphere, which is Q plus Q, divided by R squared, where we have chosen, as always, a spherical coordinate system, where this one is R, and this is the origin of this system. Great. And then there is this other shell, which is minus Q divided by R squared, because we know that these two shells, in any of these points outside the shells, basically behave as if the charge was concentrated in the origin, so they are like point-like charges in space. We've done a bunch of problems, home assignments on that. So that's the result of the electrostatic field, and of course it goes along the R direction, but these two quantities cancel out. So this electrostatic field is identically equal to 0 at each point in P, which is great, because we know that we are in microscopic electrostatic equilibrium, so we just verified for the specific case of spheres, of concentric spheres, one hollow with a thickness, which is R3 minus R2, that in this case, the field is 0. Great. Now, there was something which, when I was a student, always bugged me. So let's look at this a little bit more closely. So let's suppose to take this, this object here. So let me do two double sketches here, smaller ones. So the first one, I'm just representing again the same structure here, but instead of having the second sphere concentric, let's move it somewhere here. So now in a sudden, of course, this one is all full, this one is all full, like this, with conducting material. So now in a sudden, we have a lot of positive charge close to this region of the sphere. So there will be, without touching, a lot of negative charge in this region. Now, and when I was a student, for me it seems absolutely absurd that the motion of this inner object would not create any difference on the distribution of the charge outside, because look, what happens is that if I move this sphere from this symmetric configuration where it's easy to calculate the field and the only point capital P in this region, I move it asymmetrically. Now you cannot do this anymore, it's very complicated. So it would seem that it's impossible that in order to maintain the electrostatic field E equals 0 in this region, it seems close to impossible, almost impossible, that the external charge remains where it is. It seems like it should be more concentrated in this region so that it cancels the field here, less than there. Is this true? Well, while I cannot prove it for this jelly case because you will need partial differential equations with complicated boundary conditions, let us do it in an extreme scenario, which is the following. I'm sketching again the same object. So this is where the charge is distributed. Sorry, the charge, not the charge, where the conductor is distributed. And now let's shrink the inner sphere to just a single point. So instead of having a positive charge sphere, we have a single point like charge in space with charge plus Q. And let's put this charge, let's say, very, very close. So this is my Q larger than 0, orange. Very, very close to the surface of the sphere without touching. In this case, we will see eventually in 342 electrostatic induction a little bit more in detail and the method of images. As it turns out, it's very intuitive though, even though we're not going to do it formal in this course, it's intuitive that most of the electrostatic induction will happen where? Obviously, in the vicinity of this charge Q. So most of it will happen here. Okay, let's put like an open dot, which represents a negative charge, minus Q, approximately located in a neighborhood around this point here, Q, which is very close to the inner surface of this sphere. All right, so now we have a very non-uniform charge distribution, actually two of them, positive and negative photoelectrostatic induction here. In the limit, these are very close to each other, infinitesimally close, let's say, okay? So in the limit, I'm assuming that this distance here is infinitesimally small, dl, or if you want the dr in this case, but without touching, okay? So just a mathematical construction. This is a very non-uniform charge distribution. Will it affect the outer charge distribution? So if we had an original charge distribution in the symmetric case, so originally we started with the charge in the center, and then we move it to this region here, so there is a motion, move it, okay? So if we started with this charge distribution originally, the fact that we move it, will it change it to maintain a zero field in the shell here with some thickness? The answer is no, because let's look at the electrostatic field generated by these two charges. Well, it's nothing but Coulomb's law for a single point-like charge in space. So it's going to be, let's do it in two different colors. So the orange one is going to generate a field with this kind of field lines, etc. And interestingly enough, this other charge here will generate a field which is basically the same and basically overlapping with a negative sign to the original field, because as I said, they are very close to each other. So these very non-uniform charge distributions, which are point line charging in space, effectively those fields cancel each other, and the external distribution here plus remains completely untouched and beautifully uniform. So this is just one example that shows that if I start with a symmetric configuration, a point-like charge in the center, everything is uniformly distributed because it's all symmetric. I move it very close to the surface, to the inner surface of this sphere, in order to maintain a zero field because of ME in this object here. The external charge distribution doesn't even know that we move this internal charge, because these two charges basically kill each other without any knowledge on the external surface, all right? So this example, which is just one, again, you can prove it for more generic scenarios, but it's much more complicated mathematically, clearly shows that if I move this object, capital gamma 1, inside here, the vacuum capital omega, or if I split it into multiple parts, and as long as I maintain a charge Q, the external charge distribution is completely unaffected. All right, so to summarize this video, we wanted to understand what happens when I place a charged object within an electrostatic shield in macroscopic electrostatic equilibrium. Well, we have seen that in order to place the object inside, I need to open a channel, so I need to communicate with the external world, with the universe, to grab charge and bring it inside. Okay, so this communication channel is the one which effectively results in a positive charge on the outer skin of this object, which was originally uncharged. In order to prove all these charge distributions, we had to use Gauss's theorem, which results in total electrostatic induction, and the charge conservation principle. All right, but communication is the key. So if now, suppose that after some time we close this hole, and we forgot how we grabbed this charge and we brought it in, well, now if I move around this capital gamma 1, or I split it, etc., will this change the external electrostatic field outside the shield? And the answer is no. And I give you an example for concentric spheres with the extreme scenario of a point-like charge in space, which is a very non-uniform distribution, which clearly shows that in that example, the external uniform charge distribution is unaffected by motions of charge inside. This concept is very important because that's how we perform experiments, for example, in my lab. And in this sketch down here, you can see one of our packages. So a package is a sample holder made of a conducting material which shields the sample inside from electromagnetic radiation, which is the effect of the external world. That's it.